students, last time we have started modeling of three-phase transformer. Basically, we have started with single-phase transformer, and then we have seen how we can use that theory for modeling of three-phase transformer. So, just we will revise what we have seen in the last class. In the last class, we have seen two equations which we are written by seeing your equivalent circuit, and from these two equations we get ABCD parameters. So, what we have got ABCD parameter, this is A parameter, this is your B parameter, this is your C parameter, and this is your D parameter. So, I have written them here. Similarly, many times we need to calculate load voltage in terms of source voltage and load current. So, in that case we have defined them in terms of capital B parameter. So, this capital B parameter, which basically we calculated in last class, so that your load voltage will be modeled in terms of source voltage and your load current. So, this gives me your capital A parameter, and this gives me your capital B parameter. Then we have seen for modeling of three-phase transformer, we have seen how we can represent these quantities. Those are actually basically voltages and current in the three-phase transformers. So, we have seen that if they are grounded Y by grounded Y connections, which is shown in this particular figure, we have seen that the voltage which are generally represented by with respect to your ground terminal, that is VAN, VBN, VCN, and then current will be basically your line current, that is those are IA, IB and IC. And as I told you in the last class, we are using capital letters to represent primary side quantities. Basically in distribution system there will be high voltage side quantities. So, primary quantities will be represented by capital letters, and then similarly your line to neutral voltages on secondary side, they will be represented by VAN, VBN, VCN. Again these small letters are used for representing the secondary side. And in case of delta winding, we have seen that we can represent the line to line voltages. Those are basically VAB, VBC and VCA. Those are line to line voltages, and your line currents, which are IA, IB and IC. And on the secondary side, again it is delta connected I am considering, because it is I have written there, and then these voltages will be VAB, VBC and VCA, line to line voltages, and then line currents will be IA, IB and IC. Now, as I explained in last class, when this line current enters into transformer, windings will be delta connected. So, these currents will get divided into your delta phase windings, and then we have seen that these delta currents are represented by IAB, IBC and ICA. Those are three phase currents in the delta winding. IAB, small ab, small bc and small ca, they are basically your secondary side delta currents, and collectively I am calling them as IDABC. So, whenever I am writing IDABC, these are nothing but your delta winding currents. Then we have seen other terminologies. So, in case of transformer ratio NT, we have seen that we are representing it by rated voltage on HV side divided by rated voltage on LV side. So, to represent say turns ratio of transformer, which is delta to star, NT will be represented at V line to line voltage, because phase voltage in that case it will be V line to line voltage rated on HV side divided by V line to neutral voltage on LV side, which will basically your turns ratio in case of delta star transformer. And in case of star star transformer, it will be just line to neutral voltage on HV side divided by line to neutral voltage on LV side. Then we have seen how to represent your leakage impedance of the transformer, and we have seen that this impedance is represented on secondary side of the transformer. So, we have represented both the impedances on secondary side, and since there are three phase matrix, these are represented by diagonal element of ZT ABC matrix. Then we have seen your transformation matrix, which basically transforms your terminal voltages on the secondary side of the transformer to the terminal voltages on the primary side. To represent this, we are using this AV matrix, and we have seen that this AV matrix is nothing but your diagonal element matrix, which is having NT terms at the diagonal, and all the non-diagonal entries will be 0. So, your AV matrix will be having structure something like this. Then your AI matrix, which basically converts your line currents or winding currents on secondary side to the winding currents on a primary side. So, these are the winding currents on primary side, and these are the winding currents on secondary side, and this basically AI matrix, we have seen that it is 1 upon NT element in the diagonal, which NT is again turns ratio, and all other entries are 0. So, only diagonal elements will be present, which are 1 by NT. So, this I explained in the last class. Then we have seen that many times, since we are considering 3-phase modeling, many times we need to convert your line to line voltages to line to neutral voltages, or delta phase current to the line current and line current to the delta phase current. Okay. So, we need to know these transformation matrix so that we can easily convert them. So, last time we have seen voltage conversion. So, to convert voltages which are basically line to neutral voltages to line voltages, we have got conversion matrix which is called as D, and basically which is given by this expression. So, I had explained you last class how we get this matrix. Similarly, to convert line to line voltages to the line to neutral voltages, we have got this W matrix. We also derived this W matrix in the last class, and basically we had got this W matrix here. So, we can easily convert a line to neutral voltages to line voltages, or line to line voltages to line to neutral voltages. Again, I will tell you here, W is not equal to your D inverse, okay, but because the inverse of D is non-existence. However, whenever in expression D inverse or is will be available, in that case we can use it as a W, or whenever there is W inverse existing, then we can use D matrix. However, they are not exactly the inverse of each other. Now, we will see current conversions. In current conversions, basically many times we need to convert delta phase current to line currents, or vice versa, line means line current to the delta phase currents. One example I have shown it here. Let us see these windings which are connected in delta fashion. You can see that they are connected in loop like this, which are actually delta like this, and there are 3 terminals which A, B, C are connected to this delta, and then current IA which is coming in, current IB is coming in, and then IC is coming in. So, if you apply KCL at this point, you can write IA will be equal to IAB minus ICA, because this ICA current is coming which is in this direction, IB is going like this out of this terminal. If you apply KCL at this point, it will be IB will be equal to IBC minus your IAB, and when you apply KCL at this point, it will be IC will be equal to ICA minus IBC. Okay. If you put these 3 equation into matrix form, I will basically get this equation here, and if you observe this equation, it converts your delta currents which are represented here into the line current. So, we can I am calling this matrix K, which converts your delta phase currents to the line current. So, this is the conversion for delta phase current to the line current. Now, if you want to convert line current to the delta phase currents, it is little bit tedious task, because as I told you, in this case also the K inverse will be infinite. So, this matrix is basically singular matrix. So, if you take inverse of it, the inverse is non-existence, means I cannot say ID ABC ID ABC, which is equal to K inverse into I ABC, because K inverse is non-existent. So, we need to find out this matrix here. So, let us see how we can get this matrix, which is basically K inverse matrix. There are two cases. In case 1, if the path for 0 sequence current is not available. So, in many cases only positive sequence and negative sequence currents will be present, and there will not be path available for 0 sequence current. Like one combination which I have shown it here, in this particular transformer, this connection is actually star connection or Y connection, and this is your delta connection. So, this is Y connection in delta connection. However, this neutral is not grounded. So, this Y is having neutral ungrounded system. Since this neutral is ungrounded, there will not be a 0 sequence current into primary side of the transformer, and hence there will not be 0 sequence current, because for 0 sequence current to flow there should be always balanced there should be balancing current from the secondary winding. So, whenever 0 sequence currents are flowing in one winding, there should be 0 sequence current flowing in another winding. So, since 0 sequence currents are not there in Y here, there will not be 0 sequence current in delta. So, if the 0 sequence current path is not available, we can easily write 3 equations here. So, in this case your IA current will be nothing but your IBA minus ICB. So, if you see this IA current here, in this case this IA current will be, so this will be your IAC current and this is your IBA current. So, if I apply KCL at this point, so basically I will get this first equation here. Then if you apply KCL at another node, I will get this second equation here. And third equation we can get, since addition of all the 3 delta currents, it should be equal to 0, because 0 sequence currents are not present there. So, if you add all the positive sequence current and all the negative sequence current, since they are 120 degree displaced with each other, addition will be always 0. So, all these currents are having just negative sequence and positive sequence. Because of that, addition of all these currents will be equal to 0. So, from the addition of all the current, that is IBA plus ICB plus AC, it will be equal to 0. So, from that I can easily write by inverting this matrix, your delta phase currents will be equal to your inverse of this particular matrix into this matrix. So, if I am taking this matrix on this side by making the inverse. So, this basically gives me your line currents to the delta currents. However, there is no IC current present here. So, if you calculate inverse of this matrix, the inverse of this matrix will be given by this one. You can easily calculate it. So, and then here we do not have IC current. So, to get that IC current, what we can do, since if you observe, this last column is getting multiplied with entry 0. So, what I can do, I can make all the entries of this column to be 0 and I can put IC here. It is exactly same because IC is getting multiplied by 0 0 0. So, this contribution from that IC is not there. So, that is what I have done it here. I replace that column with 0 0 0 entry and I replace this 0 with IC. So, now we have got required transformation matrix for the case where 0 sequence currents are not present. So, we can easily convert your line currents to the delta phase current using this conversion matrix, which I am calling it as a matrix L, which is given by this particular matrix. Let us say case 2 where 0 sequence current will be present. So, I have shown it 2 cases where there is possibility of presence of 0 sequence current. So, in this case we are having again this Y delta transformer. However, unlike your earlier case, in this case I am grounding this Y connection, and because of grounding, zero sequence current path will be available. So, whenever zero sequence currents are flowing in primary winding, there will be balancing zero sequence current will be flowing in delta winding. However, if you see the secondary terminal, there is no neutral terminal available. So, all these zero sequence current will actually only flow through your delta windings. So, balancing zero sequence current will flow only through delta windings. If you see second example here, here it is I am considering delta connected transformer. So, both the sides at the line ends there will not be zero sequence current because I am not using there is no ground terminal at both the end. However, so whenever there is some zero sequence current flow through the delta winding, which are basically circulating kind of thing, then there will be always balancing zero sequence current which are flowing another delta. So, it is basically these zero sequence current only flow the delta windings in on the both the sides. So, in this case also there is possibility that negative zero sequence current will be present. So, for these cases, for these kinds of transformer, we need to found these conversion matrices which basically converts line current to the delta phase current little bit different way. So, let us see how we can calculate them. So, as I told you, if you consider this case of say delta winding where there is possibility of zero sequence current may present. So, in that case, whenever zero sequence currents are flowing, you can see that the zero sequence currents will be basically circulating and the current magnitude will be same. So, in that case your equations will be something like this. Two equations I can easily get like which we did earlier by applying KCL at this point. I will get this first equation, and after applying KCL at this point I will get second equation. So, here basically IA current which is coming out of this terminal, this IBA current is again coming towards the terminal, and your IAC current is going out of the terminal. These two equations we are getting after applying KCL at these 2 points, that is point 1 and point 2, two equations we have got. To get the third equation, we can apply KVL for the loop which I have shown it here. So, we can apply KVL to this whole delta winding loop of secondary side. So, we can easily find out. So, in this case the voltage drop across AB phase will be given by this one, which will be just the if you say VAB will be nothing but VTAB voltage at this one minus the voltage drop which is happening across the leakage impedance. So, this is nothing but VAB which is voltage at VAB terminals. Similarly, voltage at VBC terminal will be nothing but terminal voltage VTBC minus impedance drop which is happening at across the Z impedance. So, this is actually your VBC voltage, and third voltage which is VTCA minus voltage drop which is happening across this, which will be basically VCA voltage. And since the neutral is not present, addition of all the three voltages will be equal to 0. Now, what we can do, the terminal voltages we can take it together, means these three terms I am keeping on left hand side, and all these negative terms I am taking on right hand side. So, we will basically get this equation here. Now, as I told you, this terminal voltages or voltages across the winding. So, basically this VAB voltage. So, VAB voltage will be across this winding here, VBC voltage will be also across this winding, and there will be across this winding VCA on primary side, and secondary side it is VTAB, VTBC and VTCA, and this VTAB and VAB they will be just related by your turns ratio. Means I can say VT AB will be equal to VAB divided by NT, VT BC will be just equal to VBC divided by NT, and VT CAD will be equal to VCD divided by NT. And as I told you, in this case, if you add the three voltages, which are basically line to line voltages, they will be always equal to 0, because there is no zero sequence voltages present there. So, they will be just having positive sequence and negative sequence voltages, and if you add them together, addition will be always equal to 0. So, because of that, your left hand side is becoming 0 and only the right hand side is remaining. So, we got now third equation. So, 1, 2, and there is this third equation. I will just take these three equations on next slide. So, let us say this is equation number 1 which you have got, equation number 2, and then equation number 3 which you have got on last slide. I am taking it here. We can put them into matrix form. So, if we put these three equation into matrix form, I will get this term here. So, this matrix equation. Then I can take the inverse of this matrix and multiply it to this side. I will get this basically this matrix, which is basically delta phase currents, and these are actually line currents. So, we need to take the inverse of this matrix here. So, to get delta phase currents, I need to take the inverse of this matrix, and inverse of this matrix can be calculated, which comes this one. So, this is basically this inverse here. In this case also, we are now getting required currents. Here we are getting delta currents, and here we are getting line currents. However, this one term IC is missing. So, in this case also we can use same trick which we have used earlier, that is, I can make this column equal to 0, because this column is getting multiplied with 0 every time. So, I can make this column equal to 0 here, and I can put IC here. So, anyway IC is getting multiplied by 0 0. So, it will not change anything with respect to equations. So, instead of 1 1 1, I am putting it 0 here, and instead of 0 I am putting IC. So, again we have got the required matrix here, which converts your delta phase currents, line currents into your delta phase currents, in case of if there is zero sequence path is available. And I am calling this matrix which you have got here, I am calling matrix M, and this matrix M is actually basically represented by this one. So, we have got required transformations. We have got this M matrix, which is basically converts your line currents to delta phase currents. We need to use it because we are always operating on unbalanced system. So, they will not be just related by √3. So, that is why actually we need to go for this complicated matrices here, because these currents are unbalanced currents, even though angles will not be 120 degree displaced with each other, as well as the magnitudes will not be same. In this case, as I told you, when impedances are unequal, we are getting unequal drops across the terminal. However, when these impedances are equal, say this is just Z, this is just Z, this is just Z, in that case this voltage drop across each winding, it will become equal. So, in that case, when these all impedances are equal, means ZT AB equal to ZT BC equal to ZT CA, say equal to Z. In that case, all these entries will get cancelled with each other, and in that case your matrix will be this one. So, whenever equal impedances are there, this M matrix and L matrix, they will be always equal. So, this gives me line current to the delta phase current conversion. So, in summary of this lecture or last two lectures, we have seen various conversion matrices which are required, because as I told you, most of the transformer which are in distribution system, mostly they will be 3-phase transformer and they will be unbalanced, and you need to model actual 3-phase transformers. So, when you are modeling actual 3-phase transformer, we need all these conversions. So, in summary, we have got this D matrix, we have got this W matrix, which are basically used for voltage conversions. So, in case of conversion of line to neutral to line voltages, D matrix will be helpful. When converting line to voltages to line to neutral voltages, your W matrix will be helpful. And as I told you, whenever we are getting D inverse matrix, we need to use W matrix, even though inverse is non-existing. So, whenever expression we are getting D inverse, we need to replace by W. Similarly, we have got for current conversions, and two types of current conversions will required, that is, we need to convert delta phase current to the line currents or line currents to the delta phase current. So, two types of conversions are required. Converting delta phase current to the line current is easy, and for that we have seen that we can use this K matrix, we have derived also. However, when we are converting line current to the delta phase current, there are two cases exists. One is whenever there is no path available for zero sequence current, and whenever there is path available for zero sequence current. So, we have seen that whenever path is not available for zero sequence current, we have got this conversion matrix which convert line current to the delta phase currents. The conversion matrix is L, and when zero sequence current path is available, then your conversion matrix which converts line current to the delta phase current is M, and M is given by this particular expression. However, we have seen that if impedances in all the 3 phases, if they are same, generally in 3-phase transformer this condition becomes true, that is these impedances are equal, approximately equal, then this M and L matrices, they are identical or they are same. So, thank you.